Now that we know what equivalence relations and equivalence classes are, we're going to talk about some properties of equivalence classes. So we'll start off with a theorem. We're going to let R be an equivalence relation on a non-empty set A, and let A and B be elements of A. Then the equivalence class of A is equal to the equivalence class of B, if and only if A is related to B. Now, remember, an equivalence relation means that the relation is symmetric, transitive, and reflexive. So we'll be able to use those three properties throughout our proof, since R is an equivalence relation. We have a biconditional to prove, so we need to prove both directions of our biconditional. We'll start with the direction where we're going to assume that A is related to B. Now, the equivalence class of A and the equivalence class of B are sets. And to show that two sets are equal, we can do that showing both subset inclusions. So we'll first show that A, the equivalence class containing A, or of A, is a subset of the equivalence class of B. So we're going to let X be some element in the equivalence class of A. Well, then that means that X is related to A by the way we defined equivalence classes. So since A is related to B, and X is related to A, and R is transitive because it's an equivalence relation, we have that X is related to B. And by the definition of an equivalence class, then X is in the equivalence class of B. So we have our first subset inclusion. Now we want to show the other subset inclusion. So we're going to take an element Y in the equivalence class of B. Now, Y is related to B by the definition of an equivalence class. And we have that A is related to B. We've assumed that. Now, since R is symmetric because it's an equivalence relation, that means that B is also related to A. Now, since I have Y is related to B and B is related to A, I use transitivity again, and I find that Y is related to A. Therefore, Y is in the equivalence class of A. So we have both subset inclusions, thus proving that the equivalence class of A equals the equivalence class of B. Now, to prove the other direction of our biconditional, we're going to assume that the equivalence class of A is equal to the equivalence class of B, and we're going to show that A is related to B. Since our relation is an equivalence relation, it's reflexive. That means that A is an element in the equivalence class of A. Well, the equivalence class of A equals the equivalence class of B, so that means that A, the element, is also in the equivalence class of B. Therefore, A is related to B by the definition of an equivalence class. So therefore we have that A, the equivalence class of A, is equal to the equivalence class of B if and only if A is related to B. Now there's two corollaries to this theorem that I want to point out really quick. So first, if we let R be an equivalence relation on a non-empty set A, and we let A and B be elements of A, then if the intersection of the equivalence classes of A and B is non-empty, then the equivalence class of A equals the equivalence class of B. And another corollary is if we let R be an equivalence relation on a non-empty set A, and let A and B be elements of A, then A is not related to B if and only if the equivalence class of A intersects the equivalence class of B is the empty set. Let's take a look at another theorem. So we're going to have R be an equivalence relation defined on a non-empty set A. Then the set of distinct equivalence classes resulting from R is a partition of A. Now remember, a partition is a collection of subsets such that every element of A of the set is in exactly one of the subsets, and none of the sets are empty. So we're going to take a look at how we can show that the set of distinct equivalence classes resulting from our equivalence relation are in fact a partition of A. Well, each equivalence class of an element of A, say A, is non-empty because that element must be in its own equivalence class because our relation is reflexive, because it's an equivalence relation. Consequently, we also know that each element of A belongs to at least one equivalence class because we know that it belongs to its own equivalence class. Now we need to show that every element of A belongs to exactly one equivalence class. So we're going to take some element x of A and we're going to say, well, suppose it belongs to two equivalence classes. Say it's in the equivalence class of A and the equivalence class of B. Well, we've shown that if x is related to A and x is related to B, then we know that A is related to B, so the equivalence class of A is equal to the equivalence class of B. Consequently, every element of A belongs to a unique equivalence class. And we have our partition of our set. Let's take a look at an example. So I want to show that when I define a relation R on the integers by x is related to y, if 11x minus 5y is even, then R is an equivalence relation. So we need to show that R is reflexive, we need to show that R is symmetric, and we need to show that R is transitive. So we'll start with reflexive. So we're going to let A be some integer, and we're going to consider 11a minus 5a. Well, when we do 11a minus 5a, we get 6a, which equals 2 times 3a. Since 3a is an integer, then we have that 11a minus 5a is even. So a is related to a, making R reflexive. Now we need to show that R is symmetric. So we're going to assume that A is related to B, and we're going to show that B is related to A. So since A is related to B, we know that 11A minus 5B is even. So we can set 11A minus 5B equal to 2k for some integer k. So to show that B is related to A, we need to show that 11B minus 5A is even. Well, working with what we have, we can say 11B minus 5A equals the 11A minus 5B that we know something about. And to get minus 5A instead of plus 11A, I need to add negative 16A. And to get 11B instead of negative 5B, I need to add 16B. So I can get then that I have 11A minus 5B plus the quantity negative 16A plus 15B. Now, I know that 11A minus 5B is even, so I can substitute 2k in for that. And then what I have is 2 times the quantity k minus 8a plus 8b. And since k minus 8a plus 8b is an integer, then 11b minus 5a is even. Therefore, b is related to a. So I know that my relation is in fact symmetric. Finally, we're going to show that it's transitive. So we're going to assume that a is related to b and b is related to c, and we're going to show that a is related to c. So a related to b means that we have 11a minus 5b is equal to 2k for some integer k. And b is related to c means that I have 11b minus 5c is equal to 2l for some integer l. Now, adding these two together, we get 11a minus 5b plus 11b minus 5c equals 2k plus 2l. Now, we want to know something about 11a minus 5c, and we can actually solve for 11a minus 5c. When we do that, we get 2k plus 2l minus 6b. Well, that's equal to 2 times the quantity k plus l minus 3b. Since k plus l minus 3b is an integer, then 11a minus 5c is even. Therefore, a is related to c, and R is transitive. So we've shown that our relation is reflexive, symmetric, and transitive, and therefore an equivalence relation. Now, we've taken a look at the equivalence classes for this before. The equivalence class of 0 is all the even numbers, and the equivalence class for 1 is actually all the odd numbers. So there are two equivalence classes for this equivalence relation. They're defined by 0 and 1, and they partition the integers into the even integers and the odd integers. So we've talked about congruence modulo n before, but we haven't talked about it with regards to equivalence classes. So we're going to revisit this idea. So remember that when we have two integers a and b, where a is not 0, we say a divides b, and write it with that bar in between, if there exists some integer c such that b equals a times c. Also, if we have integers a and b, and n greater than or equal to 2, a is going to be congruent to b modulo n if n divides a minus b. And there we have some examples that we've actually seen before. So let's take a look at a theorem. Let n be an integer where n is greater than or equal to 2. Then congruence modulo n, that is, the relation defined on the integers by a is related to b if a is congruent to b mod n, is an equivalence relation on Z. So we can show this is an equivalence relation. We need to show that it's reflexive, symmetric, and transitive. So first we're going to let a be some integer. Now we know that n divides 0. Every number divides 0. So it follows that n is going to divide a minus a. So a is congruent to a mod n. Therefore we have that our relation. Therefore we have our relation is reflexive. Now we're going to show that it's symmetric. So we're going to assume that a is related to b. So a is related to b means that a is congruent to b mod n. So that means that n divides a minus b. So there exists some integer k such that a minus b equals n times k. Well, b minus a really equals negative a minus b, which equals negative n times k, or n times negative k. Well, since negative k is an integer, then n divides b minus a. So b is congruent to a mod n. Therefore, b is related to a, and our relation is symmetric. Now, to show that a relation is transitive, we're going to assume that a is related to b and b is related to c, where a, b, and c are integers. Now, a is related to b means that a is congruent to b mod n, and b is related to c means b is congruent to and b is related to c means b is congruent to c mod n. Well, that means that n divides a minus b and n divides b minus c. So a minus b equals n times k, and b minus c equals n times l for some integers k and l. And we can add this together, and we get a minus b plus b minus c on the left-hand side, and on the right-hand side we get nk plus nl. Well, notice we can factor n out, and we get n times the quantity k plus l. And when we add a minus b plus b minus c, we get a minus c. So we have a minus c equals n times the quantity k plus l. Since k plus l is an integer, then we have n divides the quantity a minus c. So a is congruent to c mod n, and our relation is transitive. Actually, in general, For n greater than or equal to 2, the equivalence relation of congruence modulo n results in indistinct equivalence classes. In other words, if we define A related to B by A as congruent to B modulo n, then there are n distinct equivalence classes, namely ones defined by the elements 0, 1, 2, all the way up to n minus 1. Now, when we're thinking about the elements in these equivalence classes, say we have an integer r with 0 less than or equal to r less than n. So r is one of these elements that's defining an equivalence class. An integer m is going to belong to the set that is the equivalence class of r if and only if there is an integer q, namely the quotient, such that m equals n times q plus r by the division algorithm. The equivalence class of r consists of all the integers that have the remainder r when we divide by n. So let's take a look at an example. We're going to let r be the relation defined on the integers by a is related to b if 2a plus b is congruent to 0 mod 3. Then r is an equivalence relation. So we need to again show that r is in fact reflexive, symmetric, and transitive. We're going to let x be an integer. Since 3 divides 3x, it follows that 3x is congruent to 0 mod 3. So if we substitute x for a and b, we get 2x plus x, which is 3x. It's congruent to 0 mod 3. Therefore, x is related to x, and our relation is reflexive. Next, we need to verify that our relation is symmetric. So we're going to assume that x is related to y, where x and y are integers. So we have 2x plus y is congruent to 0 mod 3. So we have 3 divides 2x plus y. So therefore, 2x plus y equals 3r for some integer r. And we can solve for y and have y equals 3r minus 2x. So if we consider 2y plus x, substituting in 3r minus 2x for y, we arrive at 6r minus 3x. Now, that's equal to 3 times the quantity 2r minus x, and since 2r minus x is an integer, then 3 divides 2y plus x. And consequently, 2y plus x is congruent to 0 mod 3. Therefore, y is related to x, and our relation is symmetric. Finally, to show that our relation is transitive, we're going to assume that x is related to y and y is related to z. Then 2x plus y is going to be congruent to 0 mod 3, and 2y plus z is going to be congruent to 0 mod 3. So 3 divides the quantity 2x plus y, and 3 divides the quantity 2y plus z. From that, we know that 2x plus y equals 3r, and 2y plus z equals 3s for some integers r and s. Now, again, adding the two sides together, we get to 2x plus 3y plus z on the left-hand side, and adding the right-hand sides together, we get 3r plus 3s. So then we know that 2x plus z equals 3r plus 3s minus 3y, or 3 times the quantity r plus s minus y. Since r plus s minus y is an integer, then 3 divides 2x plus z, or 2x plus z is congruent to 0 mod 3. Therefore, x is related to z, and our relation is transitive. Now we've seen that congruence mod n is an equivalence relation, and we've seen that the equivalence relation results in n distinct equivalence classes. Now there's some vocab that goes along with this. So, namely, we denote the set of these equivalence classes by the integer z, that one with the double line, the blackboard z, with a subscript n, and refer to this set as the integers modulo n. So if I'm looking at the integers modulo 3, what I'm looking at is the set that contains the equivalence class of 0, the equivalence class of 1, and the equivalence class of 2. And in general, when I'm looking at the integers modulo n, I'm looking at the set containing the equivalence class of 0, equivalence class of 1, all the way up to the equivalence class of n minus 1. So each element of the integers modulo n is an equivalence class. And these equivalence classes have infinitely many integers, or contain infinitely many integers. And we've already seen that this is actually all the integers that have this given remainder when they're divided by n. And because of that, we call the elements of the integers modulo n residue classes sometimes. So the same way we can define addition and multiplication on the integers and have defined it, we also have addition and multiplication in the integers modulo n. So we might expect these things to behave the same way they do on the integers, and they do more or less. So if I try to add the equivalence class containing A plus the equivalence class of B, then I should get the equivalence class of A plus B. And similarly, if I multiply the equivalence class of A times the equivalence class of B, I should get the equivalence class of A times B. So let's look at some examples and see how this actually behaves. So let's look at the integers modulo 6. Now, if I take two elements from the integers modulo 6, we'll take the equivalence class of 1 and the equivalence class of 3, and I add those together, I get the equivalence class of 4. And that actually works that way. So the integers that have a remainder of 1 added to the integers that have a remainder of 3 equal the integers that have a remainder of 4 when we're dividing by 6. Similarly, if I multiply the equivalence class of 1 times the equivalence class of 3, I get the equivalence class of 1 times 3, or the equivalence class of 3. And this again works the same way. But let's take a look at another pair. So let's take a look at the equivalence class of 2 and the equivalence class of 3. Again, the addition works, that I should get the equivalence class of 2 plus the equivalence class of 3 equal to the equivalence class of 2 plus 3, or the equivalence class of 5, and that's true. Well then, let's multiply. So I get the equivalence class of 2 times the equivalence class of 3 equal to the equivalence class of 2 times 3, or the equivalence class of 6. Well, the equivalence class of 6 is not one of the elements in Z modulo 6. But it is an element, 6 is an element in the equivalence class of 0 in Z modulo 6. So I actually have that 2 times 3, the equivalence class of 2 times 3, is equal to the equivalence class of 6, which is equal to the equivalence class of 0. So the equivalence class of 2 times the equivalence class of 3 actually equals the equivalence class of 0. Now, in similar ways, if I tried to add the equivalence class of 3 plus the equivalence class of 5, I would get the equivalence class of 8, but 8 is not, the equivalence class of 8 is not an element in Z modulo 6. So I look for the equivalence class that 8 is an element in, and I get that that's the equivalence class of 2. So the equivalence class of 3 plus the equivalence class of 5 equals the equivalence class of 2 in Z modulo 6. And similarly, the equivalence class of 3 times the equivalence class of 5 equals the equivalence class of 3. Now, we can actually put together an entire addition table for z modulo 6, or z modulo any integer, actually. And so here it is, where if I add, say, 2, the equivalence class of 2, to the equivalence class of 4, I get 0, and so forth. And similarly, I can do the same thing for multiplication.